All right, so let's talk about this problem and see what you were thinking. So I picked this one because some people actually use this identity on the test because it was on your formula sheet. So you saw another way to change things around. So if you looked, sine of 2 theta is the same as 2 sine of theta cosine theta. Did you guys notice that? All right, nice. So how does that help us? It helps us because now that 2 isn't trapped inside the sine anymore. And then we want to start to think about changing things to x's and y's. So as we change them to x's and y's, we're thinking about those formulas, right? We could change r squared to x squared plus y squared, but I don't think we want to because then we still have a sine of theta and cosine of theta, and that's gross. So instead, think about what does r squared mean? It means r times r. Right? There's a property now called the commutative property that says, hey, rearrange that however you want. It's all multiplied. So I can write that as 2 times r sine of theta times r cosine of theta. Did any of you get here to this one? All right. R sine of theta is just y. R cosine of theta is just x. So we have 2 times y times x equals 4. That looks super funky. We divide by 2x and we get that y is 4 over 2x, which is just 2 over x. Wanted you to see one where, hey, here's a formula we didn't actually do, a double angle formula, but pretty nice direct substitution there. And then seeing something different. We looked at circles and lines. This 2 over x. Can anybody tell me what shape that would make if I graphed it? Do you remember? Anybody at home remember? What shape does 2 over x make? Anyone? It's a rational graph. So where we do like the opposite corners, right, with the asymptotes, horizontal asymptote, vertical asymptote, we look for holes. That's the shape that we're looking at. So since we didn't remember and we're going to tie the calculator in anyway, let's look at how to put this in the calculator. All right. So for the calculator, we're going to do our original and we're just going to solve it for r because I think it's cool to see how it actually makes the graph. So I'm going to solve it by dividing the sine of 2 theta over and then square rooting both sides. What I have to remember when I square root both sides is that I get the plus and the minus. So there's my equation. All right, I wouldn't ask you to do one this complicated like on the quiz, clearly, but I wanted you to try. I wanted you to see something different, and let's graph it together. So even if I can't see you and your calculator, please have your calculator and try it out. Here's a reminder. If you are back in, if your calculator got back to normal mode, you're in y equals, you make sure you hit mode, you go down below radian and degree, you keep it in radians, and you want to change it to polar. Now we're going to see our y equals. All right, your calculator does not do a plus and a minus, so you have to do it as 2 separate equations. So we're going to do the positive version. Square root. I did not do square root there, that didn't work. Square root. Punch my calculator. It's okay. Then if you want to make a fancy fraction, you can, or you just use divided by. I'm going to hit alpha and F1 and get my nice pretty fraction. 4 over sine of theta. I'm going to go ahead and type in the negative version. Remember, you have to use the negative at the bottom, not the minus sign. It will not accept the minus sign.
What happened to the sine 2 of theta part?
Thank you. I was just thinking the same thing. As I was typing it in, something's wrong. Thank you. There it is. Let's bring that 2 in. That's going to make a big difference. Back up we go. There's that 2. Good eye. My calculator's mean today. So that's your other option, right? You can just use divided by. All right, you type it in, it takes a second. My app is a little feisty, which is if you have a handheld, use it. If you're here, I'm so excited to have more of you back here next week. It's gonna be very exciting. There it is. I think it's kind of cool to see the 2 halves fill in, especially if you have one of these color-coded ones. So you can see it fills in really nicely, and there's our rational graph, right? So something different that we can see in polar. Not a typical polar graph. We're not typically looking at rationals, but it's something that you can have happen. All right, so keep your calculator around because again, we're gonna start out graphing by hand. Then we're going to look at really like strictly calculator and what that can tell us about these kinds of graphs. All right, get ready. This is section 6.4. You have the notes handout to save you time, so have it open in Canny. Some of you are printing already, awesome job. And our target just says, I can graph polar equations. So I want to show you how you can graph these like normal equations we've graphed in the past. We're going to take the look today. I would say it's kind of the tedious form of graphing where we're going to plug in points and we're going to see that, hey, I can actually plot and get these graphs that we've been seeing on the calculator. And then we'll go the opposite of tedious and we'll just type in the calculator and see like, oh, look, there's the shape it is, and see what conclusions we can draw. And why are we doing this? 2 reasons. Showing you the power of math, right? Pretty cool shapes we're going to be looking at. And then number 2, to get you ready for AP Calculus. Mr. Havard and I have been talking for the past week and a half, like, hey, look, here's what I'm doing in my class. And they go just together. He sent me a worksheet yesterday so that I could do something in here that's going to get you so ready for that Calc 2, which is pretty cool. All right, check out some neat examples. Look, these are cool. Look how cool that is. Those are polar graphs. So we have here either called a cartoid or a limacon. Looks like a heart and it can turn all different ways. This is called an Archimedes spiral. This is not one that we will graph, but it is a polar graph. Pretty cool. And this one looks like a butterfly. How awesome is that? So part of this to me is just seeing how cool is that. We're not talking about a line anymore. That looks like a butterfly. That's really neat. Remembering, polar equations, we're looking at R, we're looking at theta to create these graphs, right? So the first one that I want to do with you, we are really just going to create a table of values to graph the equation R equals 3 cosine of theta. All right, so you should be looking at this chart right in front of you, right? And we're just going to fill it in together. I want to walk you through, hey, how do we do our exact values? Just like if we were picking X's and plugging them in to find Y's, that's what we're doing here, okay? We're picking thetas, we're plugging them in to get the R's. So here we go. Without further ado, R equals 3 cosine of 0. Exact values are going to be our friend here. Cosine of 0, that is our angle to the right. Cosine value, the X value is 1. 3 times 1 is 3. What does that mean for my point? It means my point looks like 3, 0. All right, doing another one. R equals 3 times cosine of pi over 6. Here's one where some of you might need to draw pi over 6. Or maybe you start to see like, okay, wait, let me pause and I can picture pi over 6 and I get root 3 over 2. So 3 times root 3 over 2 is 3 root 3 over 2. Now, when I go to actually plot that point, I don't want to try to plot 3 root 3 over 2. So I'm going to use my calculator for this, and I'm going to say, hey, let me get an approximate. So I'm going to type in 3 root 3. It worked that time. And all of that divided by 2. We'll round just to one place, because how close can you approximate a graph anyway? So we will call that 2.6. So my point I'm going to write as 2.6, comma, pi over 6. All right, if you are understanding what I'm doing and your exact values are good, keep working through. I will work through at the same time and we can compare. All right. I don't think I probably need to explain everyone, but if you're not in the mood, that's okay too. I'm giving you a head start. Whew, there's some good exact values. All right, take a minute, compare yours to mine, see if there are any that you need to write down. I'll give you a sec to do that. All right, so we're seeing another use for our exact values, okay? Finding them by hand. I'm gonna ask you to do I would call it a mini project at the end of this graphing. So let's clarify something. I would not ask you to do this on a quiz or a test. It just takes too long. But I do want you to be able to do it. I want you to be able to find our exact values and use them to do something. So at the beginning of this unit, I held up for you a poster of polar graphs. So you're not going to make a poster because you can't turn it in like that. But I'm going to ask you to do a smaller scale version of this where you are creating equations and you're actually finding points and plotting them and talking about, hey, what kind of graph is this, and making a pretty picture. It's going to be a really nice chance at this end of the marking period for something that it's going to actually count in the quiz category, but it's just something that you're going to work on. So we want to make sure, I want to make sure that you understand, what do I want? I want you to find the exact value. I want you to show me that you're thinking about what we've been doing in trig, but then that you can turn it into something that you can actually plot, right? So now let's take our exact values and let's remember and make sure that we can plot polar points. The first one says r theta is 3, 0. So our angle is 0. That's our positive x-axis. And we go out 3. There's our first point. All right, our next one is pi over 6. And we're going to go out 2.6. At pi over 3, we are 1.5. Pi over 2, we are at 0. All right, take 1 minute. See if you can get those 3 negative points in, and then we'll confirm together. All right, so we go 2 pi over 3, but then we have to count backwards. So we're actually using the 5 pi over 3 line to go our 1.5. We go here 5 pi over 6. We have to count backwards, so we use our 11 pi over 6. And then we go pi, we count backwards, we already have that point. That looks like a hexagon, doesn't it? But it's not one. So just to make sure you know, a regular function, if it's not piecewise, it can't actually give you that many jagged lines. That's not something that can happen. This is a nice circle. So we didn't want to do 50 points to make it look like a nice circle. We have these 6, and it shows us the basic shape. If we need to confirm, we can put it in our calculator. 3 cosine of theta. I come over here. We'll erase the crazy rational. And we'll type in 3 cosine of theta. Let me show you a function on your calculator that I'm going to have you use later to get a real nice picture. All right. So you type in 3 cosine of theta and hit graph. There it is. Now I showed you the square, zoom square, where it makes it look more proportional, but let me show you what we haven't used. Zoom fit. If you scroll down till you see the 0 option, zoom fit is going to change your window so that it fits really nicely. That was zoom fit. You had to scroll down to get to it. But now it's egg shaped, and this is not an egg shape. So if you do zoom fit first and then hit zoom square, then it gives you a nice zoomed in and the actual shape, right? So as we do the calculator exploration later today, I'm going to ask you to use those 2 functions together. Zoom fit, zoom square. It'll give you a really nice clear picture. So now you can see like, hey, look, there's my circle with a diameter of 3, and it looks like it's in the right place. All right. Anybody have a question about the calculator, the points, or the graph? Speak now, or I'm moving on. All right. So the only new thing we're going to add in for our second graph that you can see right on your notes, you already have all of this there for you, is checking for symmetry. And what this does, so if you can remember back to when you first were graphing just regular functions and you looked at symmetry, even and odd, is it reflected across the y-axis? because you reflect it across the origin. Basically, it helps you to not have to find so many points. So these are 3 types of symmetry that can inform what the graph looks like for you. And these, again, these come back up in calculus. I was talking to Mr. Haber, like, is this something that we should be looking at? Yeah, it is. It informs our graph and it also will help you later. So 3 types of symmetry we're going to look for. Is our graph symmetric on the x-axis, the polar axis? How do we check? We replace theta with negative theta. Is it symmetric on the line theta is pi over 2, which is the y-axis? We're going to replace r and theta with negative r and negative theta. See if we get the same thing back, the same original equation. And then to check if it's symmetric at the origin, we're going to replace r with negative r. So for each of these, we're going to be seeing, does our equation come back to its original form, right? So let's look at that for this number 2 equation, which says r equals 1 plus cosine of theta. All right, so I'm going to start out and I'm going to check for that first one, which says polar axis symmetry. To check for that, I'm doing theta and replacing it with negative theta, and I'm seeing what happens. Remember the polar axis, I'm calling it that because we're in polar, but that's just the x-axis. All right, I replace it. I have r equals 1 plus cosine of negative theta. And I need to see what happens. All right, if you look, a couple of you still have, at least Kyle has, your identity sheet in front of you, your original identity sheet. We looked at our trig functions and said, are they even or odd? What happens when I plug in a negative? If I think about it, a positive theta versus a negative theta, for cosine, cosine's the x, I keep my same value. That negative does not make a difference. So I'm going to put r equals 1 plus cosine of theta. That negative angle does not affect the value of cosine. So what just happens? I just got the same equation back, right? That means that my equation is symmetric on the polar axis. So when I find points, I'm going to be able to use that fact to get a lot more points that I don't actually have to solve for. So, you know, how fun was that to plug in a negative theta? I don't know, it wasn't super fun, but was it more fun than making a chart with 6 extra points? I would say yes. I would contend yes to that question. All right, let's check the other 2 types of symmetry and see how we do. So our next up in our list, we have pi over 2. That's our y-axis. So theta is pi over 2. We're checking for symmetry there by replacing r and theta with their negative version. And we just want to see what happens. So negative r equals 1 plus cosine of negative theta. We already found that negative theta does nothing inside of a cosine. So that is negative r equals 1 plus cosine of theta. I can tell that's not the same, but let's just get it all the way to r and prove it. I divide through by negative 1. I have r is negative 1 minus cosine of theta. All right, is that the same thing that I started with? No, it's not. So I'm not going to be able to reflect these points across the y-axis. And then the third, the final type of symmetry we're checking for is with the origin or the pole. To do that, this is a quick one. We're replacing r with negative r. And there are times when that won't make a difference in the equation. If you picture actually the one we did for a warm-up where the r was squared, the negative would go away. So that graph would be symmetric about the pole. Ooh, and that rational graph, like you can picture flipping it, doing a double flip. It's a nice example of that. So we plug in negative r here. We divide by negative 1. and that is not the same. So we cannot say that that is symmetric. All right, so we're checking for symmetry so that we know what to expect about the graph. In calculus, when you check for symmetry, you have to use it to do limits of integration and see whether you have to do a whole 2 pi or half of it. But that's what we want to be able to check with our graphs. All right, so we want to actually graph this. So you have in front of you this chart. It's the same one we did, except it's horizontal instead of vertical, giving you options. What do you like better? You'll see between these two, you pick the one you like. So here's what I want you to do. I want you to take a couple minutes. I want you to get this chart of values filled in. I want you to do them exact first. That means by hand, and then get decimal approximations from the calculator. We will compare, and then we'll plot this and use our symmetry, and we'll have this graph done, right? Take a couple minutes and do that chart. All right, check your values. So getting the exact values right is the first step. If your exact values look right, then go ahead and start plotting the points. Okay, we didn't relist them because you can see the R and the theta, but go ahead and plot the points. We'll confirm together, and then we'll see how we can use our symmetry. All right, but again, make sure you have the right values. So we go angle of 0 and we're out 2. Pi over 6, we have 1.9. Pi over 3, we're at 1.5. Pi over 2, we're at 1. 2 pi over 3, we're at 0.5. It's going to start getting sloppy looking on mine. 2 pi over 3 is our 0.5 here. Need a smaller pen. 5 pi over 6, we're at 0.1. And then we're at 0. It's in. I'll fix it. All right, so if you can see, that 1 point is kind of tiny. It's starting to curve in, right? That is not a normal shape that we have done before. If you just based what we were doing off of the first problem, then you might connect that and say, hey, I'm done. Great. It is this weird half a curve. But that is not the full shape. So let's see what it looks like on the calculator. And then let's make it happen on the graph. So our 1 plus cosine of theta on the calculator. I'm going to type that in. 1 plus cosine of theta. I'm going to hit graph. So pretty. Look at that. Sideways heart shape. All right, if yours doesn't look as pretty as mine, remember that you can hit zoom fit. Scroll down, it's option 0. If you do that though, it looks kind of oblong. So then you have to hit zoom square. I'm showing you that again because you're going to be doing it in our calculator exploration. So there's our really nice picture. So what that says is what we did isn't enough. So your choice would be, hey, either create a whole nother chart of values where you get that other half a graph, or use your symmetry. Okay, so check it out. We said that this graph is symmetric on the polar axis. That means this line here, there's our symmetry. Ooh, big symmetry. All right, that's where we're symmetric. So that means we can take each of these points and flip them over. So 0 stays, it's on the axis. Pi over 6 flips down to 11 pi over 6. We can put a point there. Pi over 3 flips down to 5 pi over 3. Pi over 2 flips down to 3 pi over 2. 2 pi over 3 flips down to 4 pi over 3. And 5 pi over 6 flips down to 7 pi over 6. So the symmetry, even though it took a moment to find the symmetry to test the 3 different types, it gave us all of those points on the graph. So now we can see, hey, I actually got the shape I was supposed to get, which is that cute little heart shape. I think that's such a cute graph. I found it exciting. All right, so idea number 1 of the day, can you graph by hand? Can you use your exact values to create one of these graphs? Can you use symmetry to help you, right? Now, what I want you to do the rest of class is going to be to look for bigger trends. So symmetry is going to help us, but we can also start to recognize, hey, what type of equation is this? What does that tell me about what I'm going to get so that I can maybe do less work, so I can know in general what I'm working with. So what you're going to be doing is you're going to be working in formative. And this is going to be all with your calculator. I'm going to ask you not to make any charts. I don't want this to be super tedious. I want this to be your calculator being really nice to you. All right, so you're going to see here, it says you will be using your calculator to discover general characteristics of 2 types of polar graphs, right? We're going to work with 2 types. Here's the first one. R is A sine theta or R is A cosine theta. And here's the general idea, and then I'll stop talking to you or at you. You can feel free to talk to me. So it says for the equations below, type the equation in your calculator and then give a sketch. A sketch doesn't mean exact, right? It means give me a nice idea of what it looks like. Make sure your calculator is in polar mode and the zoom fit, zoom square I put right there so you wouldn't forget. So when I look at the show your work bubble, there are 3 equations. You're going to type them all in. You're going to look at the graphs, give them a nice sketch. Then I ask you questions about the shape. How can you tell the radius? So you're going to actually use your graphs to try to come up with some conclusions. Then you're going to try graphs with cosine. You're going to notice some differences. You're going to try to, number 8 says, use your finding to sketch the graphs without a calculator. See, then can you actually just sketch them and then use your calculator to check? And then you're going to do kind of the same process with a really cool type of graph. Type 2 is my favorite kind of graph. They're roses. So these are going to look really neat when you type them in. Same idea. You're going to use your calculator to sketch. You're going to try to come up with the big ideas. All right. No charts here. You are not doing any more values. This is your assignment. You're going to have class to work on it. If you don't finish, this will turn into your homework. Okay. So as you look at it, thinking about now